we always start the same way with two pieces of advice. These are both good pieces of advice. And the first one is you should do problems. And the more problems that you do, the better. And the reason we ask you to do problems, encourage you to do problems, is that you learn to recognize which technique works where. Because a lot of the problems aren't really too bad at the end of the day once you know how to get started, but getting started can be the most challenging part. Doing problems will help with that. Now, the other piece of advice, take care of your health. And of course, exams are stressful. We want to make sure that when you come into the exam, you come in with your best self. We want you to come in and do great. Our goal is to get all of you to do wonderful on this exam. And we hope that's true. You're already, just you being here, I feel like that shows me that you're the good students. So thank you for being here. Health also includes mental health. So take a break. Don't study nonstop. Particularly on the day of the exam, it's good to take a short break, go out, get some air, take a walk, eat some food, stay hydrated. Not too hydrated when the exam starts, but just enough. All right, well, let's begin. Number 1, solve for y given y prime plus 2x plus 3 times sine squared y equals 2x plus 3. And y of 2 is equal to pi over 4. Okay. Now, we see a couple things right away. Well, first thing is we just see there's only a single derivative involved, y prime. That means this is a first order problem. And since this is our first order problem, we should just sort of remind ourselves that when it comes to first order, there's only a few possibilities that might occur. So the possibilities that you might see are separable, linear first order, and of course linear first order, you might say that could also be described as the integrating factor, exact, and then one other thing that you might see is substitution. Now, substitution really isn't necessarily the way to solve the differential equation. Really what substitution says is, oh, I can rewrite this up, the differential equation, into something which either becomes separable or linear first order. And we'll see examples of all of these ideas as we go along the way. So we have to start thinking about, okay, so which one do we have? Which one of these cases are we in? And, well, what are some things we can rule out really quickly? We can rule out linear first order pretty quickly because of that sine squared of y. Linear first order should have a y prime and a y, and that's it. Okay, so that's not what it is. Exact, well, this one's not exact. When we get to exact, we'll talk about they're easy to spot, and they're fun to do. Okay, so maybe separable. And when you think separable, what you'd really like to do is say, I have lots of multiplication going on. It doesn't look like we have it yet, because I see this addition sign here, but there's something else that's popping up. If you look, say, hey, this 2x plus 3 matches that 2x plus 3. Well, why don't we put those together? And also, if we're thinking separable, it's good to get the derivative by itself. So, okay, so it's not a bad idea to move that across. So, all right, so we have y prime equals, I'll put this 2x plus 3, that's this original 2x plus 3, subtract 2x plus 3 times sine squared of y. Okay. Now we say, separable, our goal is multiplication. What can we do? What happens here? We can factor. The 2x plus 3 is common, so it can come out. So it becomes 2x plus 3, 1 minus sine squared y. And now we're really very confident that yes, this is indeed separable. Okay, now we're cooking with gas, so to speak. But all right, what's going to happen here? Well, remember the y prime is just a shorthand notation, dy dx, and so we're ready to go. But before we do that, we say, well, 1 minus sine squared y. 1 minus sine squared y. Can that be rewritten in a simpler way? Cosine squared. Yes. Yes. It's one of our identities. You know, we use our identities. And we're not going to throw obscure identities at you. We gave you the good ones. All right, so here we go. We can now separate. So remember, the goal in separable differential equations, once you know you're in a separable differential equation, the word separable tells you that the main step is to separate. So you want all the y's on one side, all the x's on the other side. Well, of course, it might be y's and t's, might be x's and t's. But whatever it is, we pull them apart. So I'm going to move the cosine squared y one way, the dx the other way. So d sub y over cosine squared y is equal to 2x plus 3 dx. All right. So we've successfully separated the variables. Now we're going to integrate. Well, but before we integrate, we want to make sure we have things which are nice to integrate. 2x plus 3. Ah, beautiful. Love it. 1 over cosine squared y. Not so sure about that one. But what's another way to say 1 over cosine squared y? Secant squared. Yeah, so this is secant squared y dy. And now we're cooking with gas. We're ready. So we integrate everything. The secant squared is on our table. All right, so we have our table, and of course some of these we've done so often, we have them memorized by now. And so for instance, we know that the integral of secant squared will be tangent, and the integral of 2x plus 3 will be x squared plus 3x, and we need a constant on one side or the other. Now, at some point we need to solve for c. And we know we need to solve for c because we see that they gave us some initial conditions. So whenever they give you an initial condition, or they even explicitly state, solve the initial value problem, it means that we need to solve for c. And there's always a question of like, well, but when do we solve for c? And the answer is, we solve for c when it's convenient for us. In other words, if it's like, well, if you plugged in and you could get c pretty simply, now is a great time to solve for c. So for instance here, it says if we plug in x equals 2, we should have y equals pi over 4. If we plug in x equals 2 and y equals pi over 4, do we get nice numbers? Well, yes, we do. So we'll solve for c now. Why not? So tangent and pi over 4 is equal to, okay, so x is 2. So we have 2 squared plus 3 times 2 plus c. All right. Well, tangent of pi over 4. What's that? It is the 1. Indeed. You know, there's an old maxim that goes, you know, if a teacher asks a question, the answer is 0, 1, or somewhere on the board. When in doubt, those are pretty good to go with, 0s or 1s. But of course, there's a big difference between 0 and 1, so better to be sure. Okay, 2 squared is 4, 3 times 2 is 6, and so if I add 4 and 6, well, that makes 10. So 1 equals 10 plus c, and that tells us that c would be negative 9, because we can subtract 10 from both sides. All right. Well, we're most of the way there. What do we have? We now have that tangent of y is equal to x squared plus 3x minus 9. Are we done? No. What are we missing? There's this key phrase at the start. Solve for y. So this is a relationship for x and y. So if they said implicit, life is good, that's great. When it says solve for y, or even if it just says the word solve, it really says I have to get y by itself. Right now it's trapped inside that tangent. So how do we get it out? Arctangent. Of course you're like, Steve, you've been waiting. years to throw an arctangent up there. Of course I have. So you take the arctangent of the whole side on both sides. So arctangent of tangent, they're the inverse functions, so they undo each other. So we get that y is the arctangent of x squared plus 3x minus 9. And indeed, we have done everything. And so we're done. Done. Good. Any questions? All right. Good. Well, let's go on to number 2. Find the general form for x, given that x plus cosine of t times x prime is equal to 2 cosine cubed of t. Okay, All right, well, this will be interesting. Now, we're using different symbols, right? In the last problem, we used y prime and x. Here we use x prime and t. Does that change anything in our approach? The answer is no. No, symbols can be changed. Ideas, that's the important thing. All right, so what type of problem is this? Well, we look for the prime. We see it's attached to the x prime. So there we know it's a first order differential equation. And we start saying, well, can we figure it out? What kind? And we see, well, there's an x prime, and then there's just x. And that's the only way that x shows up. And we're like, aha! Perfect. This must be a linear first order. Good. Now you might notice they did something to see if we were paying attention. They wrote it in a different order, right? Normally they put the x prime first and then the x. Oh, they're sneaky like that. They like to see if you're paying attention. So don't let them get you. Make sure you're like, you're not going to get me that way. So, okay. So, well, first off, let's start by rewriting this in the order that we would normally think about. All right, so we have cosine of t times x prime plus x is equal to 2 cosine cubed t. All right. Now, the way that we proceed with linear first order is integrating factor. So this is, we should just make some notes here. We're going to be using integrating factor here. So we have to go through the process. Now, the first step when you're doing an integrating factor is you make sure you have things all lined up in the right place. So you want your x prime plus something x equals the other stuff. Okay, we have a problem. We don't have x prime by itself. We have this cosine of t there. So the first thing is make sure that x prime has a 1 in front of it. This one doesn't. So does that mean we have to give up? No, we're not giving up on any of the problems. We're here to get all the points. Got to get them all. Okay, so what do we do? What do we do here? Divide everything by cosine. So this becomes x prime plus 1 over cosine t x is equal to 2 cosine squared. All right, well, of course, 1 over cosine is secant. So x prime plus secant t of x is equal to 2 cosine squared t. All right, good. Now, once you have it in this form, we're ready to begin. So you grab the thing that's in front of the x. In this case, it's secant of t. And then we're going to take e to the integral of what's there. So in this case, e to the integral of secant t. This is our special piece. And now we have to ask the question, all right, well, what's the integral of secant? And you might remember it, or you might say, I don't have to remember it. I have a formula sheet, and it's on there. The integral of secant is log secant plus tangent. Sometimes people worry, do I need to stress about the absolute value signs? No, don't stress about that. You have other things to stress about, so don't worry about the absolute values. All right, so our integrating factor, updating here, since we can integrate secant, is e to natural log secant plus tangent. And when you're finding your integrating factor, don't need to worry about plus c. And what happens with e to the natural log of secant plus tangent? It becomes secant plus tangent, because e and log are inverse functions. They undo each other. So I say, great, this is wonderful. So this is our integrating factor. So this is our special piece. Now, what happens with this? Well, now what you're going to do is you're going to take this and multiply our differential equation by that expression. So we're going to get secant of t plus tangent of t, x prime, plus, I'll go ahead and multiply this, secant squared t plus secant t tangent t x equals, didn't plan very well, 2 cosine squared of t times secant t plus tangent t. All right. Now, the good news is the left-hand side is nice. It's always nice. It's why we do all of this, is so that this left-hand side, lo and behold, it becomes something wonderful. And it'll always, always, always be, you take your integrating factor, so in our case, secant t plus tangent t, times x, and then you take the derivative of that expression. So the whole point of this method is to say, hey, we're going to turn the left-hand side into something that comes out of a product rule. Okay. All right, so there we go. That's the left-hand side. Now we have to think about this right-hand side, and in particular, we have to say, well, how do we integrate such a thing? What do we do? What do we do? Well, okay, probably we'll spend a few minutes working on this. Let's multiply it through. So we have 2 cosine squared t secant t plus 2 cosine squared t tangent t. Now, I think the cosine squared t secant t, that one's probably not too bad. What happens? Cancellation. Because secant is 1 over cosine. So the first term becomes 2 cosine t. Life is good. Now the second term, well, it's more subtle. What is tangent? Sine over cosine. So we get 1 cosine to cancel, but we still have a sine left. So 2 sine cosine. Now the integral of 2 cosine, no problem. 2 sine cosine, well, we might get a little bit nervous, but then we remember, our teachers like us. They gave us formulas. And one of them says that 2 sine cosine is sine 2t. Brilliant. All right. So we have 2 cosine t plus sine of 2t. Okay, so let's just bring this one down. So we've gone to the point where we have that secant t plus tangent of t times x, taking the derivative of that, is equal to 2 cosine t plus sine 2t. All the hard work has been done. And now we just have to finish it up. We integrate both sides. And throw in a dt there. We even if you didn't, we know what you mean. All right, so the nice thing is the integral of a derivative, fundamental theorem of calculus, and of course you can't say fundamental without saying fun, so it's a really fun fact, says, hey, this left-hand side is pretty nice. Secant t plus tangent of t times x, the function we're after. And there's only one x left, so it's going to be easy to solve for x. All right, we come to this side. Well, the integral of cosine is sine. The integral of sine of 2t, well, the integral of sine is minus cosine. You have to be careful there. So minus cosine 2t. And anything else? Yeah, be careful here. Make sure you account for things on the inside. So this is, essentially it's a substitution. Anything else? plus c. Yeah, don't forget. Whenever you're solving differential equations, however many derivatives you have, that's how many constants you have to have at the end. So since it's a first order, we need to have one constant left at the end. We don't need to solve for our constant because they didn't give us any initial condition. And they said the general form. So we definitely need to make sure we have our constant in there to make sure we capture everything. So the last thing to finish it up, because it wants x by itself, we can then divide both sides by the secant t plus tangent t. And so we get x is equal to 2 sine of t minus 1/2 cosine of 2t plus c, all of that divided by secant of t plus tangent of t. Could you rewrite that? Yes. Do you need to? No. No. You know, the goal is not to say, let's guess what we think the instructors left their answers in. The goal is, let's get an answer that gets full points. And one of the instructions on the front of the exam, you know, and it's nice to read the instructions sometimes, it says, unless you're told, you don't have to simplify. And we rarely tell you to simplify. And if you do see the instruction simplify, it's going to be something glorious happens. It's going to be like, wow, now I see why they wanted it to be simplified, because it's just so cool. All right. Well, all right, so that's number 2. Any questions? I see a question.
Can we write on the left side, that would take it in, can we just write that as the simplified one?
So when we have this left side, and the question is, can we just jump to here? And the answer is yes. Yes. Now, you can, if you're paranoid, always double check. It doesn't hurt. What's a check? Well, you can check to say, if I take the derivative of this, do I get that? So for example, the derivative of secant is the secant tangent, derivative of tangent is secant squared. So that's the check. If you want to do it, that's great. If you're very confident and you like to live life dangerously, go ahead and skip that step. I'd encourage you to check things from time to time. It's a good thing to do. And I don't want you to be nervous, by the way. I should have mentioned this earlier. Don't get nervous when you see some of these problems like, oh, that seems like a really tough problem. I'm not saying that this was one of those, but later on we're going to get to like, we do the harder problems on the reviews so that when you get to the exam, you can be like, oh, thank goodness. Whew. So, all right, good. Are we ready to move on? All right, let's move on. Number 3, find the implicit solution to, and then we have a lot of stuff, almost too much to want to read, but we'll go ahead and do that. 2y e to the minus 2x plus y to negative 2/3 times y prime minus 2y squared e to the minus 2x plus x over x squared plus 1 equals 0, passing through the point 0, 1. All right. Now, you think back to what we talked about. We see here there's only one derivative. It's a first order differential equation. And you're probably thinking, well, he did separable, did integrating factor, so by process of elimination, this one must be exact. Well, that's true. It is exact. But there's other things that give it away. So a few things that give away exact is we tend to almost always include the word implicit, because for exact differential equations, you really can't solve for y. So if you see implicit, that's a clue. Now, that's not a guarantee, because sometimes separable differential equations are also ones that qualify for implicit. But very common, if you see the word implicit, you should think, okay, this is exact. The other thing that tends to happen is that exact problems tend to look like one of two things. So if you see an exact problem, they tend to look like something y prime plus something equals 0, or they'll look like something dy plus something dx equals 0. Every exact problem can be written that way. Of course, all problems can, but almost always, because we're very nice, we like our students, on an exam, we will write exact problems in this format. And so if you look at it and say, oh, I have something y prime and something equals 0. Like, that's the form for exact. So given the word implicit, given the way it's been written, we go and say, we're thinking exact right away. That's our tool. We know what we're doing. Okay, well, how does exact work? All right, well, I don't want to get too much into the theory because I have to want to teach, you know. I've got to avoid that, you know. I miss teaching. But okay, so here's how exact works. First off, we want it to look in this format here, something dy plus something dx. So this y prime, this is our dy dx. So we're going to multiply everything through by dx and rewrite it. Okay, so first step is we have our 2y e to the minus 2x plus y to the minus 2/3 dy. Then I'm going to put a plus. And I'm going to move the minus inside because I want plus something. So this minus I'm just going to move in. So minus 2y squared e to the minus 2x minus 2x over x squared plus 1 dx equals 0. Now the long-term goal of exact says what's happening is this first piece attached to the dy, it's the derivative of some big function that we're looking for with respect to y. This second piece is some big function that we don't know we're looking for with respect to x, and we're going to end up with our answer looks like that function equal to a constant c. So our real goal is to figure out the function given that we have some derivatives. This is the part that we overlap with multivariable calculus with. Now, the good news is we say, well, we have our derivatives, and we say, well, if we want our function, the way we go from derivative to function is we integrate. So we're going to integrate each piece separately. All right. So what we have is we say, well, the function f will look like this integral 2y e to the minus 2x plus y to the minus 2/3 dy. And you have to remember, this is maybe I want to say it's the tricky part, but it's an important part. When we're doing this integral, make sure what you're integrating with respect to. We're integrating with respect to y. We know we're integrating with respect to y because of the dy on the end. When we're integrating with respect to y, how do we treat x? Treat it as a constant, exactly. And as long as you remember that, that's great. So this e to the minus 2x is like a constant. So it's really like a constant times 2y. So the integral of that will become y squared. The integral of 2y is y squared, and then the constant comes along. The integral of y to the minus 2/3, all right, we add 1 to the exponent. So minus 2/3 plus 1 would be 1/3. So that would be a y to the 1/3. And then you have to divide by that exponent. So divide by 1/3. Well, divide by 1/3 is the same as multiply by 3. And then, this is the part where things get interesting, it's not a constant, it's a constant with respect to y, so it's something which can be dependent on x. So it's a constant function of x. All right. There's another integral, and we'll do that one. Integrate with respect to x. So minus 2y squared e to the minus 2x minus 2x over x squared plus 1 dx. Okay, now the y squared is a constant, and we say, okay, because we're integrating with respect to x. The integral of e to the minus 2x, well, e to the minus kx is, the integral of that is e to the minus kx, and we divide by the power. So we divide by minus 2, but since we already have a minus 2, the minus 2's cancel, so it becomes y squared e to the minus 2x. The integral of 2x over x squared plus 1, what do you do there? You can do a u sub, or this one we see so often because it's just a very convenient example. You can almost do this one in your head. So you see, if I have the bottom is x squared plus 1, the derivative of the bottom is on the top. So if you see a function on the bottom, the derivative of that function on the top means natural log. So you can go through and do the steps, But this one we would just trust you. Log of x squared plus 1 plus some function which depends on y. Okay. Now, I should pause here and say, depending upon where you learn this technique, you may have seen it done in different ways. Some people approach this in various steps where they say, okay, well, you first find this, and then you take the derivative of this expression, and you do some comparisons. I find this works really well. Now there's an important thing to do, which is we should check to see if it actually is exact. We actually haven't checked it. We're pretty confident based on the way the problem was asked. It's of the right form, but that isn't enough, because they will oftentimes be looking for this thing like, I check, this is exact. And there's two tests for exactness. And I'll do the one I prefer, which is to say I come to these two answers and I look for anything where I have pieces which have both x and y involved. So in other words, I look at these things. These parts have both x and y involved. And the thing that you check to see if it's exact is, are they the same? So, are these the same? Yes. So, these match. So, it is exact. And I will warn you that oftentimes, even if they don't explicitly say that they want you to test, they want to see somewhere that you made sure it was an exact equation. So, run the test. Don't lose any points. Got to get them all. All right. So after we've finished this, then we're almost in the home stretch. We say, okay, good. The last thing to get our fact function capital F is we now piece it together. We say, okay, we take the overlap, which is the y squared e to the minus 2x. The part with only a y, well, that's the 3y to the 1/3. The part with only an x, and that's the minus natural log x squared plus 1. And that's equal to some constant. Working our way through the alphabet, we'll go to the constant e. Okay, so now all solutions to this exact differential equation have this form for some appropriate constant. Are we done? No. Because they gave us some information. It passes through the point 0, 1. So that tells us that we need to find the right choice for e. The right choice so that when x equals 0, y equals 1. So that's what it means by 0, 1. So the way you figure out the right choice is you plug it in. So we say, okay, so everywhere I see an x, I'm going to put a 0. Everywhere where I see a y, I'm going to put a 1. So we have 1 squared e to the 0 plus 3 times the cubed root of 1 minus the natural log of 0 squared plus 1 should be e. Well, these are nice things to work with. Natural log of 1 goes away, 0. E to the 0 is 1. So it's really 1 plus 3, because the cubed root of 1 is 3. So we say, aha, e is 4. And therefore, putting it together, we get that our answer is y squared e to the minus 2x plus 3 y to the 1/3 minus the natural log of x squared plus 1 is equal to 4. And we're done. All right. Any questions? Good. Well, this is a great sign, because these are the types of problems that you'll see. You'll definitely see a couple of first-order differential equation problems, because, well, that's basically like half of the stuff that we've covered. All right, moving on to number 4. So, find y given 3y cubed y prime minus 1 over t squared plus t to the 4th y is equal to minus 2 over t y to the 4th. Okay. All right. Well, what do we do here? Well, we should note a couple of things. It is a first order differential equation, but it doesn't really fit any mold very conveniently. There's no clear path to do separation. It's not in the right form for exact that we just talked about. Is it linear first order? Well, the problem is you've got all these extra y's floating here. So it's not quite any of those. So now we're into the category that says, okay, we need to do some sort of a substitution. So let's talk about substitution, and let's just remind ourselves what we should expect. And of course, the hard part is spelling the word substitution. But when it comes to substitution problems, they fall into three categories. And they're basically, those are the only categories. If you can remember those three, you're in pretty good shape. So the first kind of substitution is Bernoulli. And this, it's really, we'll say z equals y to some power k. That's what the Bernoulli substitution is. And this will always become what we call linear first order. So this is, you use Bernoulli when it's basically the only thing you see showing up are powers of y. And as far as y is concerned, that's what I mean by powers of y. And it looks almost like a linear first order. Okay, so that's Bernoulli. The other thing we might see is what's called homogeneous. Now, unfortunately for us, this has two meanings on this exam, but we're not going to test you on vocabulary. And this substitution is of the form z equals y over x. And you can recognize it if you say, well, hey, I can rewrite everything in terms of y over x. Another way to recognize it is when you look at the original differential equation, if everything is polynomial, for example, you say, oh, all the degrees of my pieces add up to the same value. So in other words, if you add up the degree of x and the degree of y, it's always the same for all the terms. And when you make a substitution for homogeneous, you end up with separable. Now, I said there were three categories. What's the third category? The third category is the category called we tell you. All right. So those are the three categories. So if you are thinking about, this feels like a substitution problem, you should look for those three things. Now, hopefully you can find the we tell you one right away. You know, those ones are pretty clear. And so pretty much you're like, okay, if I'm thinking of substitution, I'm thinking of one of these two. All right. So which one is this? This one's going to be a Bernoulli one, because it's kind of got that flavor of a linear first order. You know, you have your y prime, something y. Well, but we got to sort of do a little bit of massaging to get there. All right, so what can we do? Well, there's a couple of things that you could do. I'm debating upon whether just to sort of like, and this is what you do, or okay, here's what I would do if I was trying to be methodical. I'll do it that way. I should do that way, right? Very methodical. So I'll get the power in front of the y prime down to, so that there's no y there term there. So I'm going to divide everything by y cubed. So 3y prime minus 1 over t squared plus t to the fourth. So I'm dividing everything by y cubed. So this will be 1 over y squared is equal to minus 2 over t y. And now I see, they did something kind of sneaky here. Well, they like doing sneaky things. You might say, well, what's the sneaky thing they did, Steve? Well, they actually swapped these pieces. So in other words, normally these would have been interchanged, but they anticipated that, like, we want to see if they are paying attention. Okay, so because I want the y prime and I want the y, so I'm going to rewrite this again, just swapping those two pieces. So it's plus 2 over t y equals 1 over t squared plus t to the 4th times 1 over y squared. And now this is what we would call Bernoulli. And this is, how do you tell? Well, if you can write in the following way, where if you could take your thumb and cover up a y to a power on the right-hand side, and if you say, aha, what's left is linear first order, you've got Bernoulli. So that's the thumb test. Can you just cover up that little piece? Does it look like linear first order? If the answer is yes, Bernoulli. All right. Now, there's a couple ways to go from here. Here's how I do it. I'm biased. I'm an old person. I have to do things which are simple. So I'll show you my ways. Use whichever way works for you. You're young. You've got great minds. And so, all right. So what I would do is now I say, aha, I'm going to clue off of this, and I'm going to multiply both sides by y squared. I want to make that a 1. And doing that, we're going to get the following. 3y squared y prime plus 2 over t y cubed is equal to 1 over t squared plus t to the 4th. And now that we've done that, the substitution sits in that spot. That's where we can figure it out. So the substitution to make here is z equals y cubed. And it will always work because what will happen is that the term with the y prime will have degree 1 less. And when you take derivative of y to power, the power goes down by 1. All right, so if z equals y cubed, z prime is 3y squared y prime. Aha! Just like right there. It's like they wanted us to succeed. So sometimes, don't get too excited about moving constants around. They put constants in good places. So be patient. Work the problem. So our problem can now be updated to say the following. We can say z prime plus 2 over t times z is equal to 1 over t squared plus t to the 4th. Okay. So we're in our linear first order, so we've put on our linear first order hat, and we go through our process again. We grab the term in front of the z, make sure that there's a 1 in front of the z prime, which we do, and we go through e to the integral of 2 over t dt. You'll see integrals like this frequently. So this becomes e to the 2 natural log of t. Well, that's the same as e to the natural log of t squared, because you can bring constants in front as powers, which becomes t squared. So the moral is we're going to multiply everything by t squared. Well, that's good news, because that was looking a little bit not great. But multiplying by t squared, all of a sudden it's looking really nice. The kind of integral you take home to meet your family. All right, 1 over 1 plus t squared. Well, of course, the left-hand side, we know by design, it's the derivative of the integrating factor times our function. So we have t squared z prime is 1 over 1 plus t squared, and we're ready to integrate. So we integrate both sides with respect to t. And what we end up with is t squared z is equal to 1 over 1 plus t squared, a classic arctangent of t plus the constant c. Do we need to worry about c? No, because there's no initial condition. So we'll just leave c as is. But we do need to find y, which means we're not done until we've gotten y by itself, which right now there's not even a y there, but that's okay. We can do two things. We can divide by t squared and then remind ourselves that z equals y cubed. So, y cubed is arctangent of t plus c, divide by t squared, and finally To get y, we use the cubed root, which, well, I do a lot of calculus, so I like to do cube roots by using to the 1/3 power. So arctangent t plus c over t squared all to the 1/3. And we're done. Done. That's it. All right, so we survived our first substitution problem. Okay. Any questions? Good. Move on to our next problem. Number 5. Find y given 1 plus log y minus log x, xy prime minus y equals y, and y of 1 equals 1. Well, what is it not? Well, we can pretty much rule out exact instantly, since it's finding y, it's not looking for implicit. It's not looking very separable because lots of adding going on. And it can't be Bernoulli because of the log. So, what do we have left? Well, notice we have log subtracting. So, this becomes log of y over x. And then at this point you're like, y over x. That's one of our substitutions. It's a classic. And so we start thinking homogeneous. All right, so this is probably a homogeneous problem. Is it? Well, we'll find out if it works. So, all right, how do we do the rest? Well, let's put 1 plus log y over x, and we have our xy prime minus y equals y. Now, oftentimes what you have when you have a homogeneous problem is you have to divide through by some power of x, so that always looks like y over x to something. Now, in this case, what that means is we'll multiply both sides here by 1 over x. So, 1 plus natural log y over x, that expression. When the 1 over x comes through, we have our y prime minus y over x is equal to y over x. All right, so this is great. We really have everything as y over x. This is perfect. This is classic textbook homogeneous. And so we're ready. Is it homogeneous? Absolutely. Okay, so how do we proceed? Well, the homogeneous substitution is to say z equals y over x. By the way, if you don't like the letter z, use whichever letter or symbol you like. But I recommend something easy to write and to follow along. Now, I like to do the following. I say, well, hey, that's y equals z times x. So then product rule, y prime is z prime times x, root of the first times the second, plus z times 1, the first times the root of the second. Now we update. So we're making our substitution. So we'll get 1 plus log z. And then here, we're going to get our y prime, which is z prime x plus z. And then minus y over x becomes z is equal to, and here is z. And we're happy because we're like, wow, it's like they planned it. The z's cancel. Well, they did plan it. I know because I wrote it. All right. I wanted it to happen. And like I said, whenever you have homogeneous, you're going to go into separable mode. Always go into separable mode. So your mindset right now, after you've started homogeneous, is everything should separate. And it's not so hard to see what's going to happen here. So we have our 1 plus natural log of z, and then we have our x from here, our dz dx is equal to z. So there's not too much that we need to move around. We need to move the z, and we need to move the x and the dx. All right, so we have 1 plus natural log of z over z is equal to 1 over x dx. And I forgot my dz. Okay, there we go. It's very small, badly written, but there it is, dz. Oh, that's really bad. I'm going to rewrite that. 1 plus natural log of z over z dz is equal to 1 over x dx. There we go. That looks better. All right, so we've separated. After separating comes integrating. And now you might say, uh-oh, 1 plus log z over z, that's not on the list. Is it possible? Well, of course. We're not going to ask you a question you can't do, I hope. Occasionally we make a mistake, but not this big. What do? How do you integrate that? It's a U substitution. So what's the U substitution to make? So sometimes a hint, notice we have a 1 over z downstairs. We say, hey, what has a derivative of 1 over z? And the answer is natural log. We say, oh, so what if we tried the following? What if we made this whole thing u? So if we did u equals 1 plus natural log of z, then the derivative would be 1 over z. So that makes the integral of 1 plus natural log of z over z dz becomes, well, the integral of u du. And can we do that one? Yes. 1/2 u squared. Okay. So that tells us that what we have is 1/2 1 plus log of z quantity squared is equal to, on this side, log of x plus c. Okay, well, we can move the 2 across. Another thing, of course, is after we've integrated, we can say, z is y over x, so I can write log of y over x. So 1 plus log of y over x squared is 2 log of x, and plus 2c, but constants can absorb constants, and so we can write it like this. All right, is now a convenient time for us to solve for c? Well, if we plug in x and y as both 1, do we get c? Because we do have initial conditions. And it looks like we have some decent conditions. So 1 plus log of 1 squared should equal 2 log of 1 plus c. But log of 1 is 0. So that says, hey, c is 1. Because 1 squared is 1. All right. So 1 plus log y over x squared is equal to 2 log x plus 1. Are we done? With the differential equations part? Yes. With the problem? No. We have to get y by itself because of the find y. So the rest of this is fun algebra. 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 Okay. We'll take the square root of both sides to get rid of the square. See, the nice thing is there's only a single y. So it's like an onion. Algebra problems are like onions. There's layers, lots of layers. We're just peeling one layer at a time. And it's also like onions. There may be some tears along the way. Okay, so we take our square root. That's our first layer. 1 plus log y over x is the square root of 2 log x plus 1. All right, subtract 1 from both sides. So, well, we'll just save ourselves some space, and we'll just do that there. All right, the next thing, got to get rid of the log. How do you do that? Exponential. So y over x is equal to e to the square root of 2 log x plus 1 minus 1. And now we're almost there. We just have to get rid of the over x. So we multiply by x. So y is x e to the square root of 2 log of x plus 1 minus 1. And there we are. Done. Exactly what we thought at. No, it wasn't exactly what we thought at the beginning. That was probably one we wouldn't have guessed. But we don't have to guess. We have tools. And tools are great because we don't have to guess. All right. Number 6. A 100-gallon tank is initially full of pure water. Nice. A tank problem. Brine. We loved brine problems last semester. Will we love them this semester? We'll know in a few days. Brine then starts coming into the tank at a rate of 2 gallons per minute. So when I read a problem like this, I like to start just drawing the picture right away, and just so, because they all have the same picture. We have our tank. It has a 100-gallon capacity, and we have brine starts coming in. So something comes in. There's the rate it goes in. So it's 2 gallons per minute. And then there's a concentration, like how salty is the water? And it says 1 pound per gallon. Now that's of course very unrealistic, but most math problems are. And at the same time, 4 gallons per minute of the well-mixed material. So in other words, this tank is mixing. So 4 gallons per minute is being drained, coming out. All right. Now, the question, determine how much salt will be in the tank when it is half full. Because remember, it's full at the start, and it's become half full. Now, how do we know it's going to become half full? Well, notice what's happening. 2 comes in, but 4 comes out. So what's happening to our water level? It's going down. And actually, let's talk about that. Of course, I said our water level. I should have said our brine level, but we're among friends. We know what we mean here. Okay, so the number of gallons in the tank at time t, we can say it's the following. Namely, it starts at 100, and because we look at the difference, 2 coming in, 4 going out, it's a net negative 2 for every minute. So 100 minus 2t. So that's an important number to keep track of. All right, so some other things. Let's come up with a function. Since we're dealing with salt, I'll use S. So S of t equals the amount of salt at time t. And we know some situations. For example, S of 0. We know that. S of 0 is 0. You might say, well, how do you know S of 0 is 0? Pure water. Pure water. No salt. Okay. So, all these problems have the same flow. So once you get that, then it actually works pretty straightforward, right? We say, look, we're after the differential equation because that's the name of our class. So we set it up, S prime, we have the rate it comes in, subtract the rate it comes out. Because when we talk about S prime, it's a derivative, derivatives are rates, and we say, look, something's coming in, something's going out, so the net rate is the difference. Now, the rate in is the easy one. We just look at these numbers. Because it's always 2 gallons per minute, it's always 1 pound per gallon. So what you do is you take the amount of the brine coming in times the concentration of the brine, and you get your rate in, 2 times 1. So a net 2 coming in every minute. Now for our rate out, that's the one, it's a little bit trickier. Okay, so what happens for our rate out? Well, we can do the same kind of thing, right? We have so the 2 is the rate at which the water is leaving, and then the 1 is the concentration. So if I think, well, what's the rate it's leaving? That's the 4. So the same way that the 2 was here, the 4 is there. The part that makes the equation the most interesting to set up is the next part we're going to write down, which is how salty is the water that leaves? Well, I need to know what kind of water is leaving, and it's the water in the tank. And so the amount of saltiness, how salty is that water? Well, you take the amount of salt in the tank, divide by how much brine there is, how much liquid there is. So the amount of salt there is S, and then you come to this part which we found, 100 minus 2T. All right. So, there we go. That's the hard part. We're pretty much halfway done. I mean, even if this was all you wrote down, you'd get a couple of points. It doesn't take a lot to get points, you know. Of course, if you want all the points, you got to keep going. But don't leave any fruit hanging. So let's clean this up. This is S prime equals 2. I'm going to go ahead and factor out a 2 on top and bottom. And because I don't like working with minuses in front there, I'm going to pull out a negative 2 downstairs. So if I pull a negative 2 out, so I'll make this a plus a 2s over 50, minus 50 plus t. So I pulled a, all right, what did I do there? I'll be a little bit careful here. So on this side, what am I doing? In slow motion. What did Steve just do? I took the denominator and I pulled the negative 2 out. So that's 50, minus 50 plus t. When you pull the negative 2 out, and then you can, negative 2 goes into negative 4 and leaves a 2. So that's how you get a plus 2s over negative 50 plus t. I should have written that as t minus 50, which I will in the next step. Okay, so brine problems always become linear first order integrating factor problems. So when you see a brine problem, it's like, aha, linear first order, integrating factor, I know where I'm going. So we rewrite this, so we have S prime, moving this across, minus 2 over, now I'll write it the way like a normal person would, because I'm not crazy. 2 over t minus 50s is equal to 2. Okay, so we take what's in front of the s, including the minus sign. We're going to take e to the integral of that expression. Well, no big surprise. We get minus 2 natural log t minus 50, which we can write this as, well, okay, the minus 2 goes up. This becomes e to the natural log of t minus 50 squared, and which becomes t minus 50, to the minus 2, to the minus 2, yeah, because we've got to keep track of the sign. All right, so that's our integrating factor. How am I doing? Any mistakes? I do make mistakes, so feel free to be like, Steve, you made a mistake, Or you're probably like, I'm going to wait till he posts it on YouTube, and then I'm going to flame him in the comments. Oh my gosh, I can't believe he can't add 2 plus 4. But all right, we move on, right? Okay, so from here, we multiply everything through. So we have t minus 50 to the minus 2 times s prime, and then it'll become here, becomes minus 2, t minus 50 to the minus 3, right, because this is really to the minus 1 power times minus 2 times s is equal to 2 t minus 50 to the minus 2. All right. Well, by design, the left-hand side is nice. Namely, it's t minus 50 to the minus 2 times s, derivative of that. And we're ready to integrate both sides. So we integrate. And what happens? Well, the left-hand side, very straightforward, our integrating factor times s. The right-hand side, the minus 50 really doesn't do anything. So plus minus a constant, substitution won't change much. So just think about it if it was t to the minus 2 power. And so what you do is you'd add 1, okay, that'd become t to the minus 1 power, and then you divide by minus 1. So you end up with a minus 2 t minus 50 to the minus 1. Now, plus C. Don't forget that. Okay. Well, is this a convenient time to solve for C? Maybe. Let's clean out the S first. So multiplying both sides through, here I multiply both sides by t minus 50 squared. We get that S is equal to minus 2 times t minus 50 plus some constant C, t minus 50 squared. All right. So, we come into our initial conditions. S of 0 equals 0. So we get that 0 is equal to minus 2 times minus 50. That's 100 plus C. And then 50 squared is, 50 times 50. And so we can subtract 100 and then divide. So we get C equals minus 100 over 50 times 50. But the nice thing is 50 goes into 100. So that's pretty good. Then both 2 goes into 50. So we end up with minus 1 over 25. So S is equal to minus 2 over t minus 50. And I can already tell that I've made a mistake. And you're probably saying, how can you tell you've made a mistake? Wait, no, I'm okay. I was worried because these are both negatives. But t minus 50 is also negative. So we're okay. It looks wrong because it's very negative. It's like, how can you have a negative amount of salt? Well, because it's not really negative. All right. Are we done? After our mild panic attack thinking we had the wrong answer. Are we done? No. Right? It feels like we should be. After you put in, enough work, you're like, I should be done. But what we found is how much salt there is at any given time. We need to find how much salt there is when the tank is half full. Okay, so we have to say, well, when is it half full? So the halfway mark will be at 50 gallons. And we say, well, when do we hit 50 gallons? We need to have 100 minus 2t to be equal to 50. And so we say, all right, well, what does that? And you see that t should be 25. So that's the time. So we're really asking how much salt is there at time 25. And it'll be after 25 minutes because time is in minutes. But this is not asking for units. So if the problem doesn't ask for units, we don't need to give them units. So S of 25, we have minus 2. If we take 25, subtract 50, what do we get? Well, negative 25. See, that's where the negative's coming in. Minus 1 over 25. And then again, 25 subtract 50 is negative 25 squared. And, okay, I did not plan my spacing well. Coming over here, we have, our answer is 50, which is this part, 2 times 25. And then notice that you get one of the 25s to cancel this, and so you end up with a plus another 25, which tells us our final answer is 75. So there will be 75 pounds of salt. If you want to add pounds, you definitely won't lose any points. But in this case, it's not asking you for units, so you don't need to. Okay. Well, you can kind of get a sense of why they like to ask these kinds of problems, because there's a lot going on. Okay, yes, I've made mistakes, or you have questions? Oh, you're being very careful there, aren't you? Oh, okay, all right. Now, we can edit this in post-production. Okay, all right, so let's double check this. Okay, so we have a minus 1 over 25 and negative 25 squared. Okay, you're right. So it's 50 minus 25. which is 25. All right, good. 25 pounds. Okay, well, does that make sense? Yes. In fact, I would have said, I would have discovered my mistake in just a moment here, because I like to say, is your answer reasonable? So, would 75 have been a reasonable answer? Well, let's think about it. That's after 25 minutes have elapsed. How much salt comes in every minute? 2 pounds of salt comes in every minute. So after 25 minutes, a total of 50 pounds of salt would have appeared. So would 75 have been a reasonable answer? No, because I would say what? Miraculously, an additional 25 pounds of salt would have had to spontaneously emerge. So, good. Well, thank you. You've saved me some YouTube comments there. All right. Other mistakes I've made? All right. Good. All right. I will try to go faster. We're going to hit some problems sooner that you can do at a quicker pace. Okay, number 7. So, 3-part problem, but all the parts are pretty straightforward. Part A, verify that this function e to the 2x and this function x plus 3 are solutions to 2x plus 5y double prime minus 4 times x plus 3y prime plus 4y equals 0. When you want to verify a solution, what do? Plug it in. That's it. That's all it says. Plug it in. Okay, so let's do part A. And we say, all right, for y1, we look at 2x plus 5, take e to the 2x double prime, minus 4 times x plus 3, e to the 2x prime, plus 4 times e to the 2x. Now, when you take a derivative of an exponential function, constants come down. So this becomes 2x plus 5 times 4e to the 2x, because 2 derivatives mean 2 comes down twice, minus 4 times x plus 3, 2e to the 2x, plus 4 times e to the 2x. Well, you can pull out the e to the 2x. And what do you have? Well, you have 2x plus 5 times 4, which is 8x plus 20. Here, you'll have 4 times 2 times x plus 3. And don't forget the minus. So this will be minus 8x minus 12. Sorry, not minus 12, because it's 2 times 3 times 4, which is 24. And then plus 4. And then you just sort of check. Well, you see, aha, I have an 8x and a minus 8x, and those cancel. I have a 20 and a minus 24 and a plus 4, and those cancel. And so you're left with 0, and so we're happy. Well, that's not the universal symbol for verified, but basically, you just have to check. When you plug it in, do you get 0? Okay, x plus 3, so we'll do y2. So we have 2x plus 5, x plus 3 double prime, minus 4 times x plus 3 times our x plus 3 prime plus 4 times x plus 3. Okay, well, the second derivative of x plus 3 is 0. The first derivative of x plus 3 is 1. And x plus 3 is x plus 3. So when you multiply this out, you'll end up with minus 4x plus 12 plus 4x plus 12. And you look at this, and it won't take you very long to convince yourself that the x terms cancel and that the constant terms cancel. So life is good, and you get 0. So any time a problem says verify a solution, you just know what's going to happen. You plug it in, carry it out, and you make sure that things work out. And you have a built-in, did I do this right, check? And the built-in, did I do it right, check is, did you get 0? And if you didn't, you just keep redoing it until you do. All right, so that's pretty straightforward. Okay, so we'll go now on to part B, which says, okay, find the solution to this differential equation. which has some initial conditions here. Now, this is not just any kind of differential equation. It's a linear differential equation. And that means superposition. So really, what part B is testing us on is, do we understand the philosophy of superposition, which says we can stack answers on top of each other. And so we say, all right, a typical solution is going to look like some constant, e to the 2x, plus some constant of times x plus 3. Well, that's our y. We find our y prime. 2a e to the 2x plus b. And we plug in our initial conditions. So y of 0 is equal to minus 6 equals a plus 3b. Y prime of 0 equals 6 equals 2a plus b. And now you get to two equations, two unknown. Definitely at some and probably more than one point in the exam, you're going to see two equations, two unknowns. So I won't belabor the point. Just make sure you're comfortable solving these. So, for instance, here, one thing we could do, we can multiply the first equation by negative 2, which would give us 12 equals minus 2a and minus 6b. And if we add this new equation to the second equation, we get that 18, 6 plus 12, the 2a's cancel, because the goal is cancellation, is equal to minus 5b. So b equals minus 18 over 5. And I know sometimes they do work out to be not the prettiest numbers, but we shouldn't be scared of fractions. You know, some of our best friends are fractions. Okay. Well, what if we wanted to solve for the other one? So we have minus 6 equals a plus 3b. In this case, what I can do is I can multiply the second equation by negative 3. So minus 18 equals minus 6a minus 3b. Whoops. And then if we add, the 3b's cancel, minus 24 minus 24 equals minus 5a. And therefore, a is 24/5. I'm not going to spend a lot of time on this step just because this is more algebra than anything. Really the key is make sure we know superposition. And so putting this together, we get y is 24 over 5 e to the 2x minus 18 over 5 times x plus 3. And that's part B. Okay. And then we have part C. So for part C, find the Wronskian. Well, all right, that can show up in a couple different places, but this one is just saying very explicitly, hey, give me a Wronskian. So the Wronskian, the Wronskian of y1, y2 is found by, it's a 2 by 2 determinant. In the first row is the functions. E to the 2x, x plus 3. The second row, the derivatives, 2e to the 2x and 1. And now, well, you take the 2 by 2 determinant. So e to the 2x times 1 would be e to the 2x. Subtract, going the other way, 2 times x plus 3, e to the 2x. Okay, so we can pull some things out. This is the same as e to the 2x, 1 minus 2x minus 6. And if we wanted to, we can say, well, that's minus 2x minus 5. And I'm going to pull the minus all the way out. So that's minus e to the 2x. And so if I pull the minus out, that becomes 2x plus 5. All right, so that's the Wronskian. Okay, so find the Wronskian, and notice there's a second part. Use this to determine the interval where the solution is guaranteed to be unique. All right, well, when we're using the Wronskian to figure out where something breaks, Where are we looking for? Yeah. Basically, the Wronskian equals 0 is where things break down. Well, can e to the 2x ever be 0? No. Can 2x plus 5 ever be 0? Yes. So our Wronskian breaks down at negative 5/2, which means that there's only a single point where our Wronskian breaks down. And where are we? Our initial condition is at 0, which is to the right of negative 5/2. So if you think about the number line. So the answer to the interval would be, you could write it as x is greater than negative 5/2, or you could write it as negative 5/2, comma, infinity. So there's our Wronskian, and there's the interval where the answer from part B is guaranteed to be unique. I see a question. It is true that if we start, okay, so from negative infinity to negative 5/2 is if we start in that interval, we'll be unique in that interval. Right, so there's two intervals. Now the question is, which interval did we start in? And that comes back to where was our initial condition at? So the location of our initial condition was at 0. So it said, well, which one of these two are we in? And the answer is we're in the one on the right-hand side. So that's why we have that interval. So it's not like we're looking for all the intervals where we have guaranteed uniqueness. It's like for our solution in particular, where are we guaranteed uniqueness? So you need to know where to start. Any other questions? All right. Number 8. Okay. We are given that f of y equals 0 for y equals -3, -1, 0, 1, 2. And, so in other words, they told us the zeros. Where are the zeros at? And for y prime equals f of y, we have that y equals 2 is stable, y equals -3 is unstable, and y equals plus -1 are semi-stable points. They didn't tell us anything about 0. Find and classify as stable, unstable, or semi-stable all the critical points of y prime equals y times y squared minus 4 f of y. Do we know what f of y is? No. Can we find it? No. Hopeless. Hopeless. Well, that's fine, because we don't have to. In fact, we say this is our favorite problem when we see things like this. The stable, unstable, semi-stable. Because those are, I call them autonomous ordinary differential equation problems. And it's just like, we just have to see the sign. We'll see the sign, and it'll open up our minds when we see the sign. Okay, so let's go back to y prime equals f of y. We know where the critical points are, so let's mark those. -3, -1, 0, 1, and 2. Okay, so those are the critical points because that's where we have equals 0. Y equals 2 is stable. So think about the arrows. If I'm stable at 2, am I going in, out, or some sort of mixture? Are they both the same? Stable, what does that mean? Stable means you go in. So if I'm stable, I head in. So what I'm doing here is I'm reconstructing the phase diagram. All right, -3 is unstable. Okay, do we go in? Do we go out? Do we go left? Do we go right? What's happening at -3? If it's unstable. Goes out. Okay, plus -1 are semi-stables. So semi-stable means you have to go in the same direction. So, for instance, since we see from -3 to -1 we're going to the right, what's happening from -1 to 0? To the right, to the right. Okay. 1 is also semi-stable. Now we see from 1 to 2 we're going to the right. So what's happening from 0 to 1? Also to the right. Oh my goodness, a lot of intervals going to the right. Okay, so we've took our information about the zeros. we told us about stable, unstable, and we got our phase diagram. But now, I want to do something else. Let's talk about the value for f of y, positive or negative. Now, if I'm moving to the right, is f of y positive or negative? I am positive, because increasing, going up to the right. So, f of y is positive anytime I'm going to the right, which is a lot of times apparently. When I'm going to the left, what's true? I'm negative, decreasing, heading to the left. So what we've been able to do is we've been able to translate this information into signs, plus or minus. Now the reason why we want to do this is ultimately when we come to classification, we have to understand what the signs are. And so we have to put things together. Now, let's talk about something else. Let's look at y times y squared minus 4. Suppose I just look at that part right now. Okay, where are the zeros at? There's that one at 0 and plus minus 2. So that's minus 2. And I want to go through and ask about the signs again. Okay, so suppose I pick a really big number, like 3, a huge number. Is this positive or negative? Positive. So y times y squared minus 4 is positive. What about a number between 0 and 2? For example, 1. Positive or negative? It's negative. So y times y squared minus 4 is negative. From negative 2 to 0, what happens? Back to positive. And what if I pick a number below negative 2? Like negative 3? Positive or negative? Negative. Okay, and now the goal is just to overlap these. So we're going to look at our pieces and we say, okay, the only points we're going to have is where f of y is 0 or y times y squared minus 4 is 0. So we end up with minus 3, minus 2, minus 1, 0, 1, and 2 are our critical points. And we want to look at our y prime equals our y times y squared minus 4 f of y. So I'm just going to go through and talk about the signs here. So make sure we split everything up so we can follow along. All right, let's start over here. We have a negative combined with a positive, which means that here the sign is, so we're multiplying together, negative times positive makes it negative, negative sign. Here we have a positive, here we have a negative, result is negative. Here we have a positive, here we have a negative, result is negative. Okay, we're very negative on this one so far. Positive, positive, result is positive. Okay, we're between minus 2 and minus 1. Up here is positive. Here is positive. The result is positive. Between minus 2 and 3, upstairs is positive. Here it's negative. The result is negative. Finally, we're negative, and we're negative. We have a positive. All right? Can you see what's going on? For each interval, we ask the question, what do we know about the sign for f of y? What do we know about the value of y times y squared minus 4? And then we multiply together. So the nice thing is, if you know the sign of each piece, multiplication, you get the sign of the whole thing. Okay, so last thing is we add in the arrows, because then it's easy. Positive is to the right, negative is to the left. So we have -3, -2, -1, 0, 1, 2. -3, what kind of point do we have? Stable. We flipped it. -2, what do we have? Unstable. -1. Semi-stable, because we head in the same direction on both sides. How about 0? Stable. How about 1? Semi-stable. And how about 2? Semi-stable. All right. That's the answer. So again, the key here is when we're classifying, really what we have to do is figure out the signs. And so the first part of this problem helps us recover, in the first sentence, these signs. Because we translate in stability into direction, directions into signs. And then we say, okay, but we also can say something about what's happening with the sign of y times y squared minus 4. Combine the information, and we get the signs of the whole thing. And with the signs, that becomes directions. Directions give us our classification. All right. And we look at the next problem here, problem 9, and we get maybe a little nervous. We say, oh my gosh, look at everything on here. It's like an essay. But oftentimes, a good rule of thumb says the longer the problem is, doesn't mean it's a harder problem. Sometimes long problems are actually very easy. So don't get intimidated. So let's see what we have here with number 9. Scientists are monitoring the total biomass of plants and animals on a tiny island by a function, which is the population, measured in tons, and t is measured in years. And their model gives that the population behaves like 20 over 1 plus 3 e to the minus 2t. Given that the scientists used the logistic model, determine the corresponding initial value problem ODE. All right. What's maybe the most important word we've seen? Is it scientist? No. Logistic. That has a very particular meaning. And what is that? Well, we turn to our formula sheet. It's one of the 2 things on our formula sheet that we picked up this semester. So the logistic model is this part. So it says, hey, if I have p prime is k p m minus p. So anytime I see the logistic model, I know that's my differential equation. Well, that tells me, hey, that says p is equal to m p0 over p0 plus m minus p0 e to the minus kmt. All right. So here, actually what they did is they gave us this part, and they're asking us to go backwards. So, okay, so we have to figure some stuff out. So another thing I just want to point out, this is an initial value problem. So we need to know p0. So we'll start with that one. How do you find p0? Well, you say, what's happening at time 0? And how do we figure that out? You plug it in. So when you plug in t equals 0, you get 20 over 1 plus 3, because e to the 0 is 1. So 20 over 4 gives 5. So the initial size of the biomass was 5 tons on our tiny island. Okay, so that's not bad. We need to figure out, so that's our initial values. We have to figure out our m and our k. So we think about, okay, how do they show up? Or another way to think about it is, what do they mean? Now, in some sense, this is testing us on, do we understand M? So how can I find M from this function? Do you know? Well, in the logistic model, M becomes the carrying capacity. It's a fancy word for it. But another way to think about it is, in the long run, that's what things go to. So if I want to find M, I ask the question, what happens in the long run? So I can say M is, well, you want to write this on a test, is what P approaches as T goes to infinity. So let's think about this. As T goes to infinity, this part, e to the minus 2t, does what? Goes to 0. So we see, aha, M is 20. So you can figure out your carrying capacity if you say, look, I know what the long run behavior of my population is. What does it approach? It approaches M. That's one of the things about the logistic model, and that's one of the things we should understand. Yes?
So if you get E naught to be 5, and then you multiply it by the 20, are you going to put 20 on top of the
Right, so you're asking the question, but if I take 5 times 20, that does not give me 20. That would be 100. See, they secretly, what they did is they found it and then they simplified it, but they didn't tell you that they simplified it. And so if you say, oh, if I now multiply both top and bottom by 5, then it becomes the right form. So the thing is, it's not just a matter of like, oh, this number here is your P naught, because who knows what simplifying they did along the way. So sometimes simplifying is useful. Sometimes it can be obfuscating. So yeah, be careful, be careful. But we're going to get all the points, right? Well, I lost a point on the mixing problem. I'm going to get all but one of the points. So, all right, so we know M. Well, how do we find our K? Well, it's useful to say, hey, there's only one place the K shows up, which is right there. So we say, well, that makes it easy. So what we can say is that our 2, which is this part, has to be our K times M. But we've already found M, so 2 is 20K, or we come to the conclusion that K is 1/10. So we put this all together, and we get the following problem. So we have that P prime is 1/10 times P times 20 minus P, and P0 equals 5. So that is the answer to part A. All right. So this was a real test of, do we understand the logistic model? Now part B. A conservation group has decided to continuously add an additional 12.5, which is 25 tons of biomass, onto the island every year. Now give the corresponding initial value differential equation that takes this into account. So in particular, that's what the EG means. It says it has both the internal growth and the imported material. So look, there's two things affecting the population. There's the logistic model, and there's the bringing stuff in. So what do? You add the two effects. So the net effect is what happens when you put them together. So 1/10 P 20 minus P plus, I'm a fraction person more than a decimal person. If I was an engineer, I'd write 12.5, but I'm a math person, so I write 25 halves. So it's the internal part, internal growth, and the import material, so that's how the population changes every year. Now, it was an initial value problem, so throw in again P0 equals 5, and then we've answered part B. So part B basically says, can you understand that, I have a small modification to my model, and how does it change? And the answer is we take both things into effect by adding the individual parts together. Now our favorite phrase, without solving. Ah, good. So we don't have to solve the differential equation we just wrote down. Ah, because that would be interesting. That would do partial fractions, and that's more for the third part of the course. Okay, so we're not going to solve it, but it says determine the limiting amount of biomass that will be on the island. In other words, find what happens as t goes to infinity. So, okay, so let's think about that. Now, previously, we said, oh, as t went to infinity, it approached m. But where did that m come from? Do you remember how you find what that m is? Like, what's special about m in this differential equation? If you plug in m, you get 0. So what's going to happen, it's going to approach a critical point. So we're really after the critical points. So, aha, this is sort of a hidden problem. That was similar to the last problem, where it's like, all right, find your critical points. So what do? Well, we're going to set p prime equals 0. So we get 0 equals 1/10 p times 20 minus p plus 25 halves. And now we start solving. Well, if we want to solve it, let's first off clear our fractions. So we can multiply everything by 10. So that would say 0 is equal to p times 20 minus p plus 10 divided by 2 is 5, and 25 times 5 is 125. Or we get that 0 is minus p squared plus 20p minus 125. Sorry, plus 125. Get out ahead of myself. I like to make what's in front of the p squared to be 1. So I'll put a negative through. 0 is p squared minus 20p and minus 125. Now, if we're lucky, and I hope we're lucky, this will factor. If we're unlucky, the quadratic formula. Are we lucky? Can we think of two things that multiply together to give 125, but add to give, well, negative 125, but add to give negative 20? Well, the thing is, 125 is 5 times 5 times 5. So there's not a lot of options. In fact, there's just 2. 125 times 1, that's never going to work. Or 25 times 5, and that does work. It's like they wanted it to succeed. Well, don't worry. If you used the quadratic formula, it would still work. Where are the signs? Minus 25 plus 5. When in doubt, just check. P squared plus 5p minus 25p is minus 20p. Minus 25 times 5 is minus 125. And so we see, lo and behold, that there are two critical points, p equals 25 and p equals negative 5. Well, which one do we head towards? If you went through and worked it out, you'd see at time 0, we're at 5. And if you plugged in, say, 0, because you can plug in anything between negative 5 and 25, you'd see that you're positive. So where do we move to? We're moving towards the 25. And so the limiting amount of biomass, the answer for part C, is 25. It didn't say units, but just for fun, we'll throw it in there. 25 tons. And of course, you might think, that doesn't seem that much because we already were going to go to 20 tons naturally. That was what M was. And then with all this extra stuff being imported, we're only getting a little bit more. Well, that's because the logistic model says if you get too big, it sort of starts collapsing on itself. And, well, conservation can be good at the start, but sometimes becomes less effective later on, I guess is the moral. Well, that's a different class. We'll talk about that. Number 10. So given that t equals 17e to the 2x minus 23e to the negative 3x is the solution to y double prime minus 4y, y triple prime minus 4y double prime plus p py prime, I am so sorry, plus qi equals 0, determine p and q. Also give the general form for solutions to the differential equation with that particular p and q. All right, so we are getting into our constant, coefficient, linear, homogeneous, and it's just a mouthful, which is a really long way to say our favorite kind of problem. And because what happens is everything becomes algebra. And I just want to make some notes here. Make sure you're comfortable with how you handle, it's all algebra, finding roots. But in particular, make sure you know how to handle repeated roots, which we may or may not see, I don't know. And make sure you know how to handle complex roots, which you, again, may or may not see. But basically, these kinds of problems always boil down to find the roots and then know how to handle what you encounter. Okay, so, there's a typo on this one. I don't know why it says t here. I'll fix that. It's a y. So y equals 17 e to the 2x minus 23 e to the minus 3x. Okay, so when you look at this, you get a little bit nervous because you look at these numbers, 17 and 23, and you're like, oh my gosh, those are big numbers. Those are scary numbers. What do you do with those numbers? You ignore them. They're just there to make you nervous. What do we really care about? The pieces here. Because we understand superposition. We understand that solutions really break apart, things being separated by plus or minus. So when we see that, I have an expression like this, like look, it's really e to the 2x and e to the negative 3x are solutions. So we have our great aha, we have e to the 2x, e to the negative 3x are solutions. And now we say, well, that's good news for us because these correspond to roots. Because remember, there's an algebra problem. So e to the 2x would say I have a root r equals 2. E to the negative 3x would say, hey, there's a root of negative 3. Now, what do I mean by the roots? Well, what we mean is our differential equation becomes algebra. R cubed minus 4r squared plus p times r plus q equals 0. Well, p and q are two unknowns, but we also have two facts. We know that r equals 2 is a solution, so that says if I plug in r equals 2, I'm going to get 0. And r equals negative 3 is a solution, so if you plug in r equals negative 3, we're going to get 0. So we do that. And so we say, okay, so if we plug in 2, we get 2 cubed minus 4 times 2 squared plus 2p plus q equals 0. If we plug in negative 3 cubed minus 4 times negative 3 squared minus 3p plus q equals 0. Back to our old reliable friend. Two equations, two unknowns. All right. Well, we know how to handle that. We'll just move the constants across, say 2p plus q. So here we have, if we just take a second, that's 8. That's 16, and we're subtracting, so it's 8 minus 16, which is negative 8 on that left side. If we move it to the right, it becomes positive 8. And now this one, well, okay. Minus 3 cubed will be minus 27. Minus 3 squared is 9. And then we times that by 4, so that's 36. And okay, so that's going to be something I'm not going to be bold and write down in one line. So okay, so minus 27 comes across as a plus 27. Minus 36 comes across as a plus 36. And we say, okay, 27 plus 36 would be 63. Yes? Okay. All right. And now we we do what we always do, look for ways to combine. The nice thing is the q's are just perfectly lined up to cancel if we subtract. 2p subtract negative 3p becomes 5 times p. Q's cancel. Then we have 8 subtract 63. Well, if you take 8 subtract 63, that would be negative 55. So p is negative 11. Okay, well, once we know what p is, then we can find q. Well, we just put in 2 times negative 11 plus q equals 8. And okay, so I can add 22 to both sides, and we get q equals 30. Okay, so p equals negative 11, q equals 30. Because that's what it said, determine p and q. All right, good. Whew. We're through the first sentence, well, first half of a sentence. All right. Now, the second part, second half. All right. So we'll block off some space here. And it said, also give the general form for solutions to the differential equation. So the thing is, we know 2 roots, because they gave it to us. How many roots are there going to be? 3. So we just have 1 root left. And once we find that root, life is good. Now, we can think of it in the following way. What we have is r cubed minus 4r squared. P is minus 11, so minus 11r. Q is 30, plus 30. So that's the polynomial we have to factor. But really, we don't have to factor very much, because we know roots. So it's going to factor into 3 pieces. The first, let's grab the root r equals 2. What's the first factor going to be? R minus 2. You know, r minus your root. The second factor, r plus 3. And now we come to our third factor, r minus something. Once we can figure out what that something is, we're done. Well, how do we do it? Where does the 30 come from? The 30 comes from multiplying the constants together. Yes? No? It's true story. True story. So we get the following. We get that 30 is negative 2 times 3 times something. Negative our question mark, if you like. Or we get that 30 is 6 times that number we're looking for. So what's our number? 5. Our number is 5. So that's our fifth root. Sorry, our third root. Our last root. One of those statements is true. Okay, so now the general form, well, looks like some constant, e to the 2x, some constant, e to the minus 3x, and then some constant, e to the 5x. Since they're all distinct, we don't have to worry about doing any bumping. No bumping involved on this problem, which is nice. No complex numbers, which is nice. And life is good. Any questions?
Not sure about what's before e to the 2x, what's after before e to the 3x.
The 17 and 23, the question is, do we not care about them? And in this case, we don't care about them. Because what we have is that these are solutions. This is essentially, what this corresponds to is like A equals 17, B equals minus 23, and C equals 0. So they gave you one solution. But then we say, well, we understand how superposition works, and we understand that these would be fed in individually. So it's like, okay, that says e to the 2x has to be a piece, and e to the minus 3x has to be a piece. So sometimes they give you stuff to sort of make you say, do you understand what these things represent? And what's important and what's not important? So the answer is, the 17 and minus 23 are not going to be involved in getting the answer. Which is kind of weird. I understand that. It's very like, but we like to make people think from time to time. At least I hope you do. Our goal is not to make you mindless computers. We already have enough of those. So, any other questions? All right. Number 11. Find a constant coefficient linear homogeneous differential equation that has general solutions of the form y equals a e to the x plus b e to the x sine squared of x plus c e to the x sine of 2x, or, briefly, explain why no such differential equation exists. Okay, well, so either we'll succeed and we'll produce an answer, or we will fail and we'll have to explain why we fail. Okay, so we stare at this for a few minutes and say, all right, well, we think about what has to be true. So what has to be true? Well, normally, when I see something where I have e to the x sine 2x is a solution, what else has to show up? The cosine, because sines and cosines always come in pairs. And so I say, hey, what about the other part, e to the x cosine 2x? And so now I get a little bit nervous. Say, okay, maybe we're in trouble. But there's something a little curious about this. What do you notice about this part, other than I just underlined it? Well, there's a trig identity, but also sine squared. Sine squared is not really what our solutions should look like. They should look like, some combination of maybe x to a power, an exponential function, and just the sine or cosine. No, like sine squared. So it's like, oh, okay. So they're trying to like mislead us by writing it as sine squared. So let's think about a better way to write this. So people mention trig identities. And we say, okay, is there a good trig identity for sine squared? Well, we look on our sheet and say, boy, it'd be nice if they gave us one, like that one. That's an identity for sine squared. So it is on our sheet. Okay. So we can replace sine squared by 1/2 1 minus cosine 2x. And now we're like, oh, cosine 2x, cosine 2x. Cool. And if we multiply this out, well, okay, so that's a e to the x plus, so here the first term would be 1/2 b e to the x, and the second term would be minus 1/2 b e to the x cosine 2x, and c e to the x sine 2x. Okay, so secretly, we say, hey, look, I can put these together. It's a constant e to the x, constant e to the x, and I'll make it a new constant. I'll give it a little hat. A hat e to the x. Here, I'll just absorb this 1/2 through, so I'll call it a b hat e to the x cosine 2x. And, well, we'll give it c. Poor c doesn't get its hat, but okay. But the moral is, our solutions look like that. So, okay, now we say, all right, they really were testing us on to make sure, do we understand what solutions should be looking like? We say, well, let's write them in a way that they should look like. Now are we okay? Our pieces look like e to the x cosine 2x, e to the x sine 2x. Are these all, is this a good set of solutions? The answer is yes. Okay, so we're happy. We're happy. So, we need to translate. Now that we have solutions, we're going to work our way back. So normally the procedure is you have your differential equation, which leads you into an algebra problem. And from your algebra problem, you find your roots. From your roots, you find your functions. That's the normal way we go. And then this problem, we're just going to be working our way back. So our functions, we need to get to our roots. So what's the root that corresponds to the function e to the x? Yeah, it's this 1 times x upstairs. So this is our root r equals 1. The cosine sine, these always come in pairs, and things get a little bit complex. What's the roots that these correspond to? So the 1, because of the 1 up in the exponent, and then plus minus 2i. Okay, so those are the roots. So now we want to go from roots to the algebra problem. Okay, so I'm going to come over here. So let's start with the r equals 1 plus minus 2i. Now, how do you get the function that gives us that? Well, I like to undo it. So I'll subtract 1 from both sides. R minus 1 equals plus minus 2i. So r minus 1 squared, because I want to get rid of the I, and the easiest way to get rid of an I is to square it. When I square plus minus 2i, what comes out? Negative 4, right, because 2 squared is 4. So you get r squared minus 2r plus 1 equals negative 4, or r squared minus 2r plus 5 equals 0. In general, I'll just say if you have a plus minus bi, then this is coming from r minus a squared plus b squared. That's where that root comes from. Okay, what about the r equals 1? Okay, so we have our r squared minus 2r plus 5. Those are our complex roots. And r equals 1 is r minus 1 equals 0. Okay. Are we done with our algebra yet? No. We need to expand. So we'll multiply through. R squared times r is r cubed minus r squared minus 2r squared. I'm just multiplying everyone from the first times everyone from the second. And so let's see, that was minus 2r squared. Okay, now we are up to minus 2r times minus 1 is plus 2r. 5 times r is 5 times r. And 5 times minus 1 is minus 5. Or r cubed minus 3r squared plus 7r minus 5 equals 0. So now we're to the algebra problem. So our last step is the differential equation. And for that, well, we just remember that the powers are how many derivatives? Y triple prime minus 3y double prime plus 7y prime minus 5y equals 0. And so that is the constant coefficient linear homogeneous differential equation where all the solutions can be written in that form. Normally they'd be written in that form, but they could be written in that form. All right, good. Any questions? Okay, in that case, on to number 12. Another, well, kind of word problem. Now, you should expect some kind of wordish type problem. Generally speaking, they fall into 3 categories: a population, a mixing, or a spring. So one of those 3 things will show up, either a population, a mixing, or a spring. So we've already done a population problem, we've already done a mixing problem, so it's only fair that we do the trifecta and do a spring problem. So we have a spring mass damper. Some books say spring mass dashpot. Some people just say spring mass system that has been set up with a mass m equals 4, a damper with damping constant c equals 8, and a spring with spring constant k equals 5. Now, the thing is, you should just say, look, I know all the spring mass damper systems. There's a basic differential equation. You have your mx double prime, think mass times acceleration. Your damper, which is attached to C, your damper is going to be associated with velocity, so that's c times x prime. The spring constant, well, that's Hooke's law, so that's just attached to k times x. And then you have your external force, but no external force is mentioned, so you set it equal to 0. All right, so in our case we say, okay, our mass is 4, our c is 8, and our k is 5. So 4x double prime plus 8x prime plus 5x equals 0. Okay, so that's our differential equation. So that's an important step. Make sure you know the form. Give the general form for motion of the spring. In other words, solve the differential equation. And it doesn't give us initial conditions, so we're going to end up with constants, which is great. Then finally, also determine if the system is underdamped, critically damped, or overdamped. Okay, so let's get into solving. Algebra, right? 4r squared plus 8r plus 5 equals 0. Okay, we can try to factor. We try. We've just failed. All right. After failing, factoring, what do we do? Quadratic formula. Now, of course, you can give more of an effort before you go to quadratic, or you can just go straight in. No harm either way. Okay, and so, we even put the quadratic formula on the equation sheet, so it's good to use it sometimes, right? All right, so r equals negative b, so in our case, negative 8, plus minus the square root, b squared, 64, minus 4 times a times c, all over 2a, so over 8. Okay, so 4 times 4 times 5 would be 80. So we have negative 8 plus or minus 64 minus 80 is negative 16. So we have a negative inside our square root. Square root of negative 16 gives us 4i. So we end up with negative 8 plus or minus 4i over 8. Oh, and of course we can divide through. And so that would be negative 1 plus or minus 4 over 8 is a half. Okay, so we talked about constant coefficient, linear, homogeneous, and that's what a spring a spring mass system is. And in this case, we have complex roots. So that says our roots say we're going to have things which involve sines and cosines. So x, we're going to have some constant a. The real part goes in the exponential function, so it's e to the minus x. And then the imaginary part goes inside the trig function, so cosine half x. And then, of course, we have to do sine, cosine pair. So b, e, real part, so minus x, sine, imaginary part, 1/2 x. And that is the general form. We don't have to solve for a and b, no initial conditions. Okay. Now, as far as it comes to damping, you should think of it in the following sense. Underdamped is complex roots. So if you have complex roots, you're underdamped. Now, essentially what you should think of as underdamped, you still spring. You're still going up and down. So complex roots, that still means you look like a sine curve. So you still go up and down. So that's why we call it underdamped. Overdamped, when you turn your damper way up, so your shock absorbers are super high, these are distinct real roots. Oops. I said the word distinct, and then I said did it again. Maybe I shouldn't talk while I write. Distinct real roots. And so essentially you should think of it as, it's very rigid. It doesn't bounce at all. There's no up, down. You got rid of it. Critically damped is essentially right between the two. And it's the ideal amount of damping to a system, but that's a different story for another day. And you should think of this as the repeated real roots. And so for me, I just remember what goes on. So I just remember underdamped means I'm still moving up and down. So if I see sines and cosines, I'm underdamped. Overdamped says I've gotten rid of all the up and down. And so, but they're distinct real roots. So, and then critically damped is the repeated roots. So for us, we see sines and cosines. So we are under damped. And you don't have to justify it. You just say what it is. Okay, classic Steve move here. I wrote this as x equals a e to the minus x cosine half x plus b e to the minus x sine half x. But wait, can't have x and x. That's wrong. All right. It should be x equals a e to the minus t cosine half t plus b e to the minus t sine half t. So be careful. Be careful. Switching around your variable names, it can happen, so watch out. All right, but otherwise, we're good. Okay, let's keep going back to our normal flow. Okay, so that brings us to our final two problems. The end. The end is near. But I'm going to say that with high confidence, that on the exam, you will have at least one problem that looks like one of these two. Now, what are these last two problems dealing with? These are the last thing that we learned about, which are second order, linear, non-homogeneous differential equations. So be prepared, and I will tell you from experience, last semester, this is the problem that sank a lot of students. In some sense, it's the one you have the least practice with, so it's understandable. But don't let that happen to you. So be prepared. Don't be worried. Don't be nervous. Don't be scared. Be prepared. So let's go through this. So find the solution of y double prime minus 4y prime plus 3y equals 4x e to the x plus 6. Satisfying y of 0 equals 2 and y prime of 0 equals negative 5. Now, okay, so I've already said we're in our non-homogeneous setting, and other than non-homogeneous being a hard word to spell, the good news is you automatically know there's two options that might be available. One option is the undetermined coefficients. In essence, it's like, well, we basically know what it looks like, except there might be some constants we have to solve for. The other option is variation of parameters. So it's always going to be one of these two. That's it. This is the only two tools we have. So a little bit of rambling here. Between the two, if undetermined coefficients is available, take it. Last semester, it was an undetermined coefficient problem. And most people saw that it was undetermined coefficients that got it right, and they used that way. Out of all the people who did variation of parameters, maybe, I'll say 100 people, maybe 50 to 100 people, everybody who tried variation of parameters got it wrong, with one exception. And in case you're wondering who's the one, they're the person who now does the review sessions on Sunday and Monday. We're like, you got it. I believe in you. So, this is just my way of saying, go with undetermined coefficients if you can. So how do you know if you can? All right, so let's talk about that. So undetermined coefficients are easy to identify. you need constant coefficients, which we have, and things that look like what we want. So in other words, things that look like they come out of constant coefficient problems. Do we have constant coefficients? Yes. Does this look like things that come out of constant coefficient problems? Yes. We are going with undetermined coefficients. We're not even going to touch variation of parameters on this one. But okay, spoiler, there's one more problem. So you can kind of guess what the next one is. All right. So how does it work? Well, the idea for this is we say we have our solution is going to come in two waves. We have the y sub c, which is the complementary part of the solution. And you should think of this as the homogeneous part. And this is the this handles initial conditions. And so that's why we throw it in there. And then we have the y sub p, and this handles the non-homogeneous part. So that's why we keep that in there. So each one has its own role, and between the two of them, we capture everything. Okay, so you always have to find, no matter which one you're doing, you always have to find the homogeneous solution first. And so we start with a relatively warm-up problem. Y double prime minus 4y prime plus 3y equals 0 becomes r squared minus 4r plus 3 equals 0 because we have that flow. Return differential equation becomes algebra. Algebra we solve. Should factor. It does. R minus 1, R minus 3. So our roots are 1 and 3. Which says that our complementary solution looks like something e to the x, something e to the 3x. Okay. And you'll notice I'm being very conservative because I know that there's still more to do. All right. Now comes maybe the harder part of the problem, which is to say, what does yp look like? So you come to yp and you say, well, what are the pieces? There's two pieces. So one piece is this x e to the x, and this other piece is 1. Now, there's a couple things you have to go through. There's a process to say, all right, there's the things I see, but there's also the things that are missing that need to be included. So just looking at this as our right-hand side, we say, okay, sines and cosines have to come in pairs, but there's no sine and cosine. Life is good. If I ever see an x to a power attached to something, I've got to have x to all lower powers. You see that x there? So what else do I need to include? E to the x. So normally, initial guess, so here's our, I'll say initial, would be some constant, well maybe I won't use a because I've already used a here, some constant x e to the x plus some constant e to the x plus some other constant. Okay, that's our initial guess. And so in other words, okay, again, just repeating the process, you grab the pieces, make sure you have anything with lower powers of x if you need it, make sure sine cosine comes in pairs. Now I said initial, because now you have to be careful. Now you look and say, look at my pieces I have, does anything overlap with y sub c, which is why you have to find yc first. And I notice that there is an overlap. Okay, so if there's overlap, what do? We bump. So, in this case, we need to bump our e to the x's, and we bump all the e to the x's up by 1. So, our real guess for y sub p is cx squared e to the x plus dx e to the x plus e. The e is attached to the 1. It doesn't overlap, so it doesn't need to be bumped. Okay, this was the hard part. Because finding the homogeneous is becoming mechanical at this point. And then what we do after this is mechanical. It's just making sure we have the right form. Okay, so what comes after this? Well, the thing is, it's a solution. if it's a solution, we plug it in. We put on our verify hat. And so we're going to toss in this expression into that differential equation. And this is, well, okay. Let's take our derivatives just underneath here. So we have to do some product rule. So 2cx e to the x plus cx squared e to the x. Here we'll have d e to the x plus dx e to the x. And then that term goes away. Yp double prime. Okay, again, product rule, 2c e to the x plus 2cx e to the x. That's the first piece. Here, 2c x e to the x plus cx squared e to the x. And then we have a plus d e to the x plus d e to the x plus dx e to the x. Okay. Well, you know, like I said, this one is probably going to be harder than what you see on the test, but it's good to see harder ones. I should point out that you can group things. So you could bring the yp as c times x squared e to the x plus 2 times c plus d times x e to the x plus d times e to the x. In a similar way, yp double prime becomes c times x squared e to the x plus, here we have 4c and then a d x e to the x, and then we have a 2c and a 2d e to the x. Okay, we now plug these in. So we have y double prime c x squared e to the x plus 4c plus d x e to the x plus 2c plus 2d e to the x. Y double prime minus 4 y prime, which is c x squared e to the x plus 2c plus d x e to the x plus d e to the x plus 3 y cx squared e to the x plus dx e to the x plus e. Okay. Whew. I know there's a lot we just wrote down, but I want you to not be like, I just wrote down a lot. I want you to think, okay, it's just procedural, it's mechanical. Again, the hard part, the critical part is getting the y sub p. After that, it's just plugging and being careful to keep track. Now, what happens here? Well, what happens here is we group. So, the x squared e to the x's. Let's work on those. Here we have a plus c. Here we have a minus 4c. And here we have a plus 3c. X squared e to the x. Okay, what about x e to the x? Well, we have a 4c plus d minus 4, because remember this 4 distributes through along with the minus. So minus 4 times 2c plus d x, I forgot my 3d x e to the x. What about e to the x? I should have been switching colors here. Okay, so the x e to the x and the e to the x. All right. We have our 2c plus 2d. Then we have minus 4 times d, which is that part. And then we don't have anything, so that's all right. And that's our e to the x. And finally, good, it's nice to get near the end, we have our 3e. Okay, now what's the punchline? The punchline is that this whole expression is the 4x e to the x plus 6. So we compare coefficients. This 3e, what does it have to pair up with? It has to pair up with the 6. Aha! Good news. E equals 2. The c minus 4c plus 3c, what happens there? It's 0. If it didn't become 0, we probably made a mistake because there isn't an x squared e to the x term there. All right, but it automatically became 0. In fact, it doesn't tell us anything. All right, how about this term, the 2c plus 2d minus 4d e to the x? Well, what does it match up with on the right-hand side? It's 0 because there is no e to the x term. So this part equals 0. Now that says that 2c minus 2d equals 0. What does that tell us about c and d? That says c and d have to be the same. C equals d. Okay, and now we come to this one, which first off, let's clean this up. We have 4c minus 8c, which is negative 4c. We have d minus 4d plus 3d, which is 0d. So this simplifies to minus 4c. Minus 4c has to match with what? The 4. So this has to match with 4. Minus 4c equals 4. So what is c? So c is negative 1. Good, good. So we now have our c, we have our d, we have our e. So that says our particular solution is, well, c is minus, so it's minus x squared e to the x. D is a minus x e to the x. And e is a plus 2. Okay. So, are we done? No. All right. Can we finish before we run out of paper? Maybe. I don't know. But now we can come back and say, okay, we know our answer is the complementary part, which we just found, which we found earlier, and the particular part, which is what we just found. So our general solution looks like a e to the x plus b e to the 3x plus, well, I should say minus x squared e to the x minus x e to the x plus 2. So that's our solution. Our general form for our solution. Now are we done? No. Because what have we not taken into account? Initial conditions. Okay. But the good news is the end is in sight. So, we find y prime. So y prime is, well, it's a e to the x plus 3b times e to the 3x. And then we have some more stuff, minus 2x e to the x, minus x squared e to the x, minus e to the x, minus x e to the x, and then the 2 goes away. Okay, so plugging in our initial conditions, y of 0, the good news is 0 is an easy number to plug in. We'll get a plus b, 0, 0, plus 2 equals 2. Okay, so that really tells us, oh, a equals negative b, because the 2's cancel, so a plus b equals 0, a equals negative b. Y prime is 0. Well, we get a plus 3b, 0, 0, minus 1, 0. Okay, so a plus 3b minus 1, and that equals, minus 5. All right, so remember that A is negative B. So if I replace A by negative B, then this becomes minus B plus 3B is 2B. Or is it not 2B? That is the question. Oh yeah, it is 2B. Okay, minus 5, you add 1, becomes minus 4. So what is B? Negative 2. What is A? Positive 2. So we then put those in. So our final answer is y is equal to 2e to the x minus 2e to the 3x minus x squared e to the x minus x e to the x plus 2. And done. Now you're thinking, are you sure you wanted undetermined coefficients, Steve? And I'm like, yes, it fit on a page. That's how I know. Variation of parameters would not fit on a page. All right. Any questions? I know when you see an answer like this, you're just like, I guess I'm going to make this one of my problems I drop. No, I don't want you to think that way. I really want you to be like, okay, there's a procedure. Find the homogeneous part, figure out what my YP looks like, run it through, like you're just saying, I'll just run my verification, plug it in, and solve for your coefficients. That's why we call it undetermined coefficients. And then solve for initial conditions if you have it. Sometimes you don't have it. Okay, so this is kind of a worst case scenario. And again, the ones on the exam, you should say, are not worst case scenarios. They will be more friendly. Our final problem. And thank you so much for being so patient. I'm sorry I've gone on. I will learn to speak quicker. The good news is, if you're watching this online, you can play it at like 1.5 speed. And I've been told I almost sound like a normal person. Okay. So, number 14. Find the general solution for x squared log of x squared y double prime minus 2x log of x y prime plus 2 plus log x over y equals 2x squared log of x cubed over x squared plus 1, given that the YC, they gave us the complementary solution. A log x, b x log x. Okay, we know it's not homogeneous because of that part. It's second order. So second order says, okay, we're not using any of our first order tools. Don't try like integrating factor or separable, nothing like that. It's not homogeneous because we have this piece here. Notice that these are not nice looking pieces. As soon as you have something that strays out of e to the x signs and x to a power, undetermined coefficients is thrown out the window. We are forced. We have no choice. We must use variation of parameters. Okay. But the good news is there's a formula. Now, this one uses x as where we have y here and t where we have x here, but we can just do the conversion. We're smart people. So if we just replace here your x's by y's and your t's by x's, it says your particular solution looks like, I'll move this to the side here so we can see it while I write. You take minus y1 integral of y2 times f over the Wronskian of y1, y2, and dx plus y2 integral y1 times f over the Wronskian y1, y2 dx. Okay, so we'll put that aside. So we have to figure out a couple things. What is y1? What is y2? What is f? What is the Wronskian? All right, let's just make the easy things. y1 and y2 are the solutions to the homogeneous part. In other words, they're the pieces of your y sub c. And they gave it to us. And there's a reason they gave it to us. And the reason they gave it to us is we have no hope of finding it. It's a very good reason they gave it to us. All right, so now we have our y1, y2. Let's do our Wronskian. So the Wronskian of y1, y2. So it's log of x log x. The derivative of log x is 1 over x. The derivative of x log x is log of x, because it's derivative of the first times the second, plus x times 1 over x, which is 1. So I did the product rule for taking the derivative of x log x. All right, carry out the math. We're going to get log of x times log of x plus 1, so that's, I'll just write it out, log x plus 1. Subtract 1 over x times x log x. And we see it's not looking too bad. Log of x squared plus log of x minus log of x leaves us with log of x quantity squared. All right. The only thing we haven't said yet is what is f? Now, the fact that I'm delaying the answer to that should make you suspicious. So if I ask you, is that f? You might be inclined to say yes. But the fact that I'm now making a big show of it, you're going to want to say no. Is that f? And why not? It's not f. What's the problem? What's in front of y double prime? Stuff. What needs to be in front of y double prime? No stuff. We need to get rid of that. How do you make that go away? Divide it. So really, our f is actually this divided by what's in front of y double prime. So it's 1 over x squared log of x squared times 2x squared log of x cubed over x squared plus 1. So the nice thing is you get some cancellation here. The x squareds cancel, some log of x's cancels, so you end up with a 2 natural log of x over x squared plus 1. So that's actually what f is. Okay, so now we have f. So we have all our pieces. We have the formula. So the rest of the problem is mostly just carrying out this computation. So let's carry it out and call it a night. Or if you're watching it in the daytime, we'll call it a day. So minus y sub 1 minus log of x integral y2 x log x times the function 2 log of x over x squared plus 1, and then divide by the Wronskian. Well, okay, I can put that as a log of x squared. So this is the Wronskian, this is our f dx, plus y2, which is our x log of x, integral y1 log of x, our f, again, 2 log of x over x squared plus 1, our Wronskian, log of x squared dx. Do you notice anything? The logs all cancel. It was almost as if they wanted you to be able to integrate. Because they do. You should be suspicious if you're like, this is not integrable. Check your work. For example, if we hadn't realized that f actually needs to be fixed, we would have gotten something that just is impossible. And we'd be like, our teachers don't hate us that much. Let's check our work. So x log x integral 2 over x squared plus 1 dx. Okay, so let's do these two integrals. What's the integral of 2x over x squared plus 1? ln of x squared plus 1. We did that earlier. What's the integral of 2 over x squared plus 1? Well, the 2 comes out. 1 over x squared plus 1, the integral is? Arctangent. Oh, yes, somebody has really picked up the, yeah, Steve likes arctangent. Woo! Yes. Well, it turns out that there's not a lot of interesting functions where both the function n times x are integrable. Okay, now, is this our answer? It is our answer for y sub p. What are we after? Good news, no initial conditions. Phew! Okay, but we are after the general solution. So what's missing here that doesn't make it the general solution? Y sub c. So our answer will be y, which is y sub p plus y sub c together. So minus log of x times log of x squared plus 1 plus 2x log of x arctangent of x plus a log of x plus bx log of x. Done. Done. You know, we dropped the proverbial pen. All right. Well, thanks for coming. I'll be here for a few more minutes if you have questions, and good luck on the exam.